Imagine being hundreds of feet underwater, sealed inside one of the most complex and survivable warships in service, where mistakes in engineering or maintenance can have catastrophic consequences. Life aboard a nuclear-powered submarine depends on redundant safety systems, constant drills, and crews trained to react without hesitation. In 2025, these vessels face growing challenges: drones, undersea surveillance networks, and adversaries advancing in ways that make hiding harder than ever. How do they stay submerged for months? And how close are new sensors to finding them? To answer that, we first need to look at the fleet itself. The 2025 Submarine Fleet. The US submarine fleet in 2025 is far smaller than the sprawling force fielded during the height of the Cold War, when both Washington and Moscow built submarines at a relentless pace. Instead of competing on sheer production numbers, today's Navy operates with about 64 total nuclear-powered submarines, split between roughly 50 attack submarines, SSNs, and 14 ballistic missile submarines, SSBNs. Though the force is lean compared to Cold War levels, every boat now carries far more capability, giving each vessel a reach and flexibility that older generations could not match. This reduction in numbers might look like a disadvantage on paper, but the calculus has shifted. The priority is no longer massing hulls across every ocean corridor. It's maximizing what a single submarine can accomplish. A modern SSN can deploy with advanced sonar, arrays able to detect and sort contacts at ranges unthinkable in the 1980s. Add in the ability to fire not just torpedoes, but precision land attack and anti-ship missiles at long distances, and each submarine suddenly represents multiple roles rolled into one. Its nuclear reactor allows it to remain submerged for months, limited only by food supplies, and new computing power enables crews to process real-time acoustic signatures with an accuracy their predecessors would have struggled to imagine. Where early Cold War submarines often needed numbers to overcome limitations in endurance and sensors, the modern fleet flips that logic. A single Virginia-class submarine on patrol today can carry out intelligence collection, sea denial, precision strikes, and undersea escort missions simultaneously. The result is fewer submarines covering more tasks with greater survivability and versatility. In short, capability now outweighs quantity. This emphasis on advanced capability has made deployment patterns even more strategic. Attack submarines in the Atlantic chiefly monitor Russian fleet activity and protect key maritime routes into the Arctic, where ice cover complicates navigation and detection. Their counterparts in the Pacific focus on the Indo-Pacific region, where vast distances and expanding Chinese naval activity force the US to carefully position each deployment. Ballistic missile submarines likewise divide between coasts, some slipping quietly into patrol boxes in the Atlantic, others heading into the wide expanses of the Pacific. The guiding principle is the same as it has been for decades. Keep them unpredictable, keep them hidden, and deny adversaries any certainty of where they might be. Managing this force of about 64 submarines, however, is not without strain. Every deployment must be balanced with training, maintenance, and shipyard availability. If boats are stuck in overhaul for months longer than scheduled, fewer remain available for patrols at the same time that global security demands continue to rise. Both Russia and China represent persistent undersea challenges, but China's rapid naval growth in particular stretches the US fleet across larger contested regions. Every submarine assigned to one area means another region has less coverage. Fewer hulls, more responsibility, and greater pressure if yards or crews fall behind. Long-term sustainment also comes down to production. Two programs dominate the future of the fleet: the Columbia-class ballistic missile submarine, which will replace the aging Ohio-class, and the Virginia-class, the backbone of the attack submarine force. These two classes together anchor the Navy's shipbuilding plan, but industrial capacity limits how quickly new submarines can be built. Delays in either program ripple through the entire force structure, underscoring how closely America's ability to project undersea power depends not only on the submarines at sea, but also on the shipyards that maintain and replace them. Strategically, this means each submarine carries weight far beyond its own hull. With only about 64 boats in total, the loss of even one would be felt sharply, both in military value and as a signal to adversaries. To offset that vulnerability, the Navy invests heavily in survivability. Quieter propulsion systems, hardened hulls, and highly trained crews drilled to react instantly to mechanical failures or unexpected contacts. The logic is simple. If each submarine is irreplaceable in the short term, then each must be as close to invulnerable as possible in practice. In the bigger picture, the transformation of the fleet illustrates a paradox. On paper, America has fewer submarines than at any point in half a century. In reality, the force of 2025 commands a level of reach and capability that no competitor can equal. One ballistic missile submarine on patrol today wields the destructive power of thousands of older strategic warheads, while an attack submarine carries enough weapons and sensors to replace several Cold War-era boats at once. Numbers alone no longer define strength. Effectiveness and adaptability now do. The Navy has chosen quality over quantity, but that choice makes understanding the roles of these vessels even more important. The fleet divides into very different kinds of submarines, each built for a distinct purpose. Some take the fight forward, tracking adversaries and striking targets with precision. Others exist to vanish, staying unseen for months while carrying weapons designed never to be used unless the nation's survival is at stake. The difference between these two types of submarines is central to how American undersea power works, and why both are indispensable today. Attack submarines versus ballistic missile submarines. The submarine force is divided in two: the attack submarine, or SSN, the prowling predator, and the ballistic missile submarine, or SSBN, the silent vault. Each fulfills a completely different job, and their behaviors at sea reflect those differences. One is built for speed, stealth, and weapons that strike first. The other is built to disappear, waiting quietly with a payload it hopes never to use. Attack submarines act as the hunters of the deep. They move into contested waters ahead of larger fleets, clearing out threats before crises erupt, and ensuring that US surface ships can operate where they're needed. They are armed with heavyweight torpedoes, Tomahawk cruise missiles, and with the Virginia payload module on newer boats, the capacity to carry up to 40 Tomahawk-sized weapons, an upgrade that has fundamentally expanded their strike role. This makes them flexible. A single SSN can sink enemy submarines, launch precision land attacks, or insert special operations forces onto a hostile coast. Crews drill endlessly in contact tracking and target identification because mistakes in fast-moving environments are costly. Their effectiveness rests on hearing everything without being heard themselves. Ballistic missile submarines, by contrast, are designed for endurance and invisibility. There are 14 of them in today's fleet, all Ohio-class, with the Columbia-class scheduled to replace them beginning later this decade, eventually reducing the number to 12. Their armament is not measured in torpedoes or cruise missiles, but in Trident IID-5 ballistic missiles. Each missile carries multiple nuclear warheads that can reach across continents. Once deployed, an SSBN patrols quietly for months on end, its location known only to a select group of naval planners. Its mission is not to go near adversaries, but to remain at large, extremely difficult to detect, and therefore nearly impossible to eliminate in a single strike. This guarantees what strategists call a credible second strike capability, the assurance that the US could retaliate even if attacked first. The technology upgrades in 2025 reflect these dual roles. Attack submarines now employ sonar systems that use digital signal processing to separate faint contacts from the background noise of the ocean. They can identify signature patterns of foreign ships and submarines with greater speed than crews could manage in earlier generations. When combined with expanded missile payloads from the Virginia payload module, SSNs can execute both intelligence missions and precision strikes at long range without having to approach a coastline. Their prowling nature means they remain forward deployed, close to possible conflict zones, capable of quick and flexible response. SSBNs, on the other hand, have benefited most from refinements in quieting technology. Newer designs use reactor systems that avoid mechanical pumps, reducing vibration. Hull coatings and acoustic tiles prevent the reflection of active sonar pulses, while internal systems are isolated to minimize noise travel through the water. The result is not invulnerability. No submarine can claim that, but a platform engineered to be extremely survivable and exceptionally hard to track. Their quiet operation brings credibility to their mission. They deter nuclear conflict not by what they do, but by making it impossible for adversaries to know where they are. To make this distinction concrete, consider two simultaneous patrols. Near Taiwan's contested waters, an American SSN silently monitors the growing presence of Chinese surface groups and submarines. Its crew notes propeller rhythms, sonar emissions, and radio traffic patterns, building a database of movements. If conflict erupted, the submarine could launch torpedoes against hostile submarines or long-range missiles against shore facilities. Its strength comes from being close, unseen, and ready to attack on short notice. Meanwhile, thousands of miles away, a ballistic missile submarine continues its long, monotonous patrol. Its crew follows strict routines, running equipment checks and navigation drills, but avoids high-traffic regions. They do not seek contact. Their purpose is to sustain endurance under the ocean's cover, maintaining an option for nuclear retaliation that no opponent could eliminate with certainty. Its silence is the threat. The very possibility of its hidden presence discourages adversaries from escalation. When viewed side by side, the missions reveal a simple contrast. Attack submarines project power in conventional conflict. They announce US presence in subtle ways, reminding adversaries that any surface ship or submarine could be marked and followed without detection. Ballistic missile submarines guarantee deterrence by staying submerged and unpredictable, their weapons reserved for scenarios of last resort. The two are halves of one strategy: hunters that secure the seas day to day, and vaults that anchor strategic stability at the nuclear level. Crew life also reflects the divide. On an SSN, sailors work through high-tempo missions filled with constant contact reports and a stream of tactical decisions. A deployment may involve trailing adversary submarines for weeks or operating close to foreign coastlines. The pace is quick, and the margin for error is slim. By contrast, an SSBN crew trains for repetition and precision. Watches can stretch into long periods of routine monitoring where little changes. But every mechanical check must be perfect, because the weapons aboard must remain reliable even after months beneath the surface. One crew lives in bursts of action, the other lives in disciplined endurance. Modern attack submarines are expanding further into intelligence roles. They can launch unmanned undersea vehicles to scout or monitor regions where human presence is riskier. They intercept communications and map undersea terrain, serving as information gatherers before any conflict begins. Their range and adaptability make them more than just combat vessels. They are tools of surveillance, reconnaissance, and forward presence, extending US awareness into contested seas without signaling overt aggression. Ballistic missile submarines change less, but their upgrades focus on staying viable against rising anti-submarine technology. Even as nations deploy new undersea sensor networks and unmanned patrols, boomers improve their reactor designs, hull coatings, and quiet propulsion systems in order to remain ahead. They are not expected to expand missions. Their only task is deterrence, and their continued ability to vanish into patrol areas validates their existence. Understanding this contrast, Hunter versus Hidden Vault, explains why the US maintains both. Removing either half would create gaps adversaries could exploit. Submarines that only hunted could not deter nuclear conflict. Submarines that only carried nuclear weapons would concede control of contested waters. Together, they create a layered security, one part visible through controlled demonstrations of power, another entirely invisible, promising retaliation if anyone miscalculates. But neither the prowling predator nor the silent vault could exist without one shared technology that underwrites everything about their endurance, their stealth, and their reach. Without it, submarines would have to surface constantly and expose themselves. To understand how they can vanish beneath the ocean for months at a time, we need to look inside the system that powers them every moment they are underway. Inside the nuclear reactor. The unbroken rhythm of submarine operations is sustained by one source of power that makes everything else possible: the nuclear reactor. Unlike conventional boats that must return to the surface often, nuclear-powered submarines draw their endurance from a compact reactor designed to run continuously while sealed deep beneath the ocean. Instead of days measured by battery life or fuel reserves, nuclear propulsion stretches that timeline into months. The ability to stay underwater for entire seasons isn't just convenient, it is what makes the submarine survivable. Stealth enduring through time is the real advantage. Nuclear propulsion at sea is not the same as nuclear power plants on land. The massive civilian reactors often associated with skyline cooling towers have little in common with their naval counterparts. On submarines, reactors are built to be compact, self-contained, and able to operate in a closed steel envelope under enormous pressure. They must keep turning without interruption, often for years at a time, while producing enough power to move thousands of tons of metal silently through the ocean. To an adversary, that power source is invisible, but its presence extends the submarine's shadow far beyond what fuel-burning engines could provide. The contrast with diesel-electric submarines shows why this matters. Diesel boats still play important roles in many navies, but their architecture limits them. Every few days they must either surface or snorkel close enough to the air to recharge their batteries. Whenever that happens, the risk of detection from radar or aircraft sensors spikes. The act of surviving becomes tied to routine exposure. A nuclear submarine sidesteps that problem entirely. Seamlessly submerged for months, it eliminates the very signatures that often betray conventionally powered submarines. For decades, submarine reactors needed refueling during their lives. Each cycle involved major overhauls in specialized shipyards, stretching maintenance into months and decreasing fleet availability. Modern designs move away from that pattern. The Virginia class, for example, was engineered to lower the frequency and complexity of midlife refueling, while the Columbia class, the next generation of ballistic missile submarines, takes it further. Its reactor core is designed to last the full service life of the submarine without requiring a midlife refuel. That reduces downtime, improves availability, and shifts the entire maintenance model of the fleet. It also demonstrates how advances in fuel efficiency and reactor control have reshaped the balance between endurance and logistics. The underlying principle remains the same: generate heat from the fission of enriched uranium, transfer that heat into water to create pressurized steam, and use the steam to turn turbines. Those turbines generate electricity and drive the propeller system. What has changed are the refinements around safety, efficiency, and stealth. Modern boats carry overlapping layers of emergency systems built to take over instantly if a component falters. Sensors track temperature, pressure, and radiation parameters with precision, feeding continuous data to trained reactor operators. A deviation from expected performance generates immediate warnings. The result is not a plant running unchecked, but a system built around control and redundancy, never left without safeguards or human oversight. A major evolution in recent years has been the shift toward quieter propulsion. Traditional systems linked steam turbines directly to propeller shafts through reduction gears, an arrangement that introduced both vibration and distinctive acoustic traces. A newer approach replaces that mechanical link with an electric drive system. In practice, turbines generate electricity, which then powers motors that turn the propellers. This reduces machinery noise and creates smoother thrust, making detection by enemy sensors far more difficult. The Columbia class will incorporate electric drive from the start, representing a design focused as much on stealth as on power. For submarines, noise is vulnerability. The less they radiate outward, the more secure their patrols remain. The power created by the reactor extends far past propulsion. Everything sustaining life inside the sealed hull depends on it. Oxygen is drawn from seawater through electrolysis, splitting hydrogen and oxygen so crews can breathe continuously without outside air. Carbon dioxide scrubbers remove exhaled gases to maintain a safe atmosphere. Water required for drinking and cooking comes from desalination plants, again powered by the reactor, converting seawater into fresh. These functions once demanded large logistics trails for surface ships. For submarines, they come automatically as long as the reactor hums. Food, not water or air, becomes the limiting factor. Modern patrols frequently run around 90 days, not because energy is depleted, but because pantries eventually empty. Temperature control also flows from that same power source. Heat within the confined hull builds quickly, not only from the reactor itself, but also from the constant operation of equipment and electronics. Unlike a building on land, a submarine does not shed excess heat naturally. Active climate regulation keeps spaces livable for crew and stable for sensors and weapon systems. Lighting, communications, cooking, and computing all follow the same rule. If it requires energy inside a submarine, it flows from the plant located deep amidships. In that sense, the reactor binds together the warship as an organism. Every function circles back to that single core. Despite the advanced automation and safeguards, reactor operation depends on watchstanders. Nuclear-trained sailors spend years in study and simulation before their posting, memorizing protocols and emergency drills until they become instinct. Their daily work might look uneventful, minor adjustments, close tracking of displays, valve checks, but concentration is constant. The burden is clear. A serious mistake would not only threaten the submarine, but could compromise deterrence and national security. Vigilance preserves the secret endurance of the ship. The unbroken hours of monitoring are the price for silent months at sea. Space inside the hull is another dimension improved by modern reactor design. Earlier generations devoted vast compartments to bulky machinery and shielding. Progress in miniaturization and efficiency has compressed those systems, freeing critical space for alternative uses, additional sensors, expanded weapon storage, or simply less cramped crew quarters. On a platform where every inch carries a purpose, such efficiency magnifies capability across the boat. Another consequence of efficient design is flexibility. The freed weight and space translate into room for payload modules and evolving technologies meant to keep submarines relevant through decades of service. Endurance itself creates paradoxes. Submarines technically could keep moving underwater indefinitely as long as the crew has food. Yet patrols are scheduled with precision. Long deployments stretch human resolve, and extended confinement inside a steel shell taxes both body and mind. Routine maintenance, rotations, and supply-resupply require scheduled returns. Thus, a vessel that could theoretically sail for years between refueling remains tied in practice to quarterly calendars shaped by people more than reactors. The machine is ready. The crew demands balance. By 2025, nuclear propulsion demonstrates how design choices ripple outward into strategy. Reactors that avoid midlife refueling extend availability. Electric drive augments stealth. Life support integration allows missions measured in months instead of days. The overall effect is to give one submarine the ability to patrol far from home waters without reliance on supply ships, tankers, or escorts. Independence in endurance means independence in strategy. Commanders can send boats into contested waters confident that detection will not come from a need to resurface. Quiet power alone guarantees that advantage. It is easy to frame this as purely a story of engineering. The miniature plant sealed inside a submarine hull, circulating quietly while missions unfold. Yet the reactor is also the enabler of what comes next. A submarine with endurance, but no means of force, would remain little more than a science experiment. The energy that powers propulsion and life support also drives the systems that load, maintain, and fire weapons. Every torpedo launch, every missile strike, Every sonar sweep traces back in some way to the same nuclear plant. What transforms quiet endurance into a credible weapon system is how that power supports the tools of combat. Inside the same hull that houses the reactor lie weapons designed for precision and reach, able to threaten adversaries in ways they cannot always see coming. That shift, from propulsion to lethality, defines the next step in understanding how modern submarines fight. Advances in weapons systems. Weapons define what a submarine can actually do in combat, and by 2025, the systems carried on board have become far more advanced and flexible than earlier generations. Torpedoes, cruise missiles, and new experimental technologies give today's submarines an arsenal that can reach ships, land targets, and even potential high-speed threats, all deployed from beneath the surface without warning. The centerpiece of that arsenal remains the heavyweight torpedo. The US inventory is still anchored by the Mark 48, but the weapon today has evolved into a very different machine than when it first entered service decades ago. Modern Mark 48's trail guidance wires back to the submarine, allowing operators to steer the weapon and feed it targeting data through the closing stages of an attack. Onboard processors supplement that link by analyzing sonar returns, helping the torpedo discriminate between genuine contacts and decoys. In its final approach, it can maneuver aggressively, switching between passive listening and active sonar pings to ensure a strike. That combination of operator control and autonomous adjustment is why the weapon is so effective. A target cannot easily trick the system with simple noisemakers. The wire maintains communication until the very last moments, and once cut, the weapon hunts independently until detonation. Instead of smashing directly into a ship's hull as in earlier designs, these torpedoes are built to disable with precise under-keel explosions that compromise a vessel's structural integrity. For large surface warships, the effect can be decisive, and a single successful hit may be enough to remove the ship from combat altogether. Noise control has become vital for torpedo effectiveness. Launch signatures that were once fairly obvious now generate far less turbulence and sound. This makes it harder for an enemy vessel to know it has been targeted until the weapon is already inbound. When every second counts in deploying countermeasures, that margin gives the submarine a clear advantage. The quiet nature of modern launches has become just as important as the destructive mechanism at the end of the torpedo's path. Alongside torpedoes, cruise missiles have defined the submarine's offensive reach. The Tomahawk missile has been the workhorse of long-range strikes for decades, and its current versions incorporate significant upgrades. The missile remains subsonic, but guidance systems now allow mid-course updates, retargeting, and more sophisticated mission planning. Certain models are configured for anti-ship roles, giving submarines a standoff capability against moving surface fleets. Others retain extended range land attack capacity, enabling underwater launches against fixed facilities and infrastructure far inland. Integration with submarine handling systems ensures these missiles remain practical to load and store. The Virginia-class submarine's design includes vertical launch tubes compatible with Tomahawk-sized weapons, and newer blocks add the Virginia payload module. This module dramatically increases the number of cruise missiles that a single submarine can carry, multiplying strike capacity far beyond the earlier baseline of 12 tubes. With the addition of VPM, a single Virginia-class boat can load several dozen Tomahawks, representing a significant boost in offensive firepower independent of surface strike groups. Emerging technology introduces the potential for hypersonic weapons, but by 2025, their place on submarines remains tentative. Prototypes and test launches have occurred, and some navies are pursuing concepts of undersea hypersonic deployment, but operational fielding is still limited and experimental. These weapons promise speeds above Mach 5, compressing the response time for any defense system and making interception difficult. But it is important to note that as of now, they are a developing capability rather than a standard feature of the fleet. For submarines, the near future may see their gradual incorporation, but current strength still lies in torpedoes and Tomahawk cruise missiles. Command and control over these weapons remain bound by strict procedure. For conventional torpedoes or cruise missiles, submarines execute orders under established rules of engagement. For nuclear-armed platforms, the safeguards grow tighter. Launching a strategic weapon requires multiple layers of authentication, with two-person verification procedures inside the submarine, ensuring no single individual has sole authority. Crews train constantly on the actions necessary to carry out an order: loading, programming, firing. But the actual authorization always comes from higher command. In practice, submariners focus on execution rather than selection of targets, and layers of oversight reinforce both safety and control. Adversaries have not stood still. Countermeasure systems attempt to disrupt the torpedo's path with decoys, acoustic interference, or even defensive interceptors. This is why wire guidance remains so central. While older torpedoes might have been fooled into chasing loud noisemakers, today's weapons can confirm acoustic profiles, receive direct steering input, and cut through deception before closing in. When combined with quieter propulsion systems and improved onboard processors, the balance still favors the attacking submarine. The practical effect of these weapons is to turn every submarine into a multi-role platform that can force caution across wide areas. A Mark 48 launch can neutralize an enemy submarine in contested waters. A battery of Tomahawks from a Virginia class can hit shore facilities hundreds of miles inland without warning. And while hypersonic technology is not yet widely deployed, the fact that it is being tested signals to potential adversaries that new levels of speed may soon join the mix. For fleet commanders, the uncertainty of submarine armament complicates planning. A surface group must assume that any detected US submarine in the area could put ships under torpedo threat. Coastal defenses must assume that Tomahawk missiles could arrive from an unseen launch point far offshore. This unpredictability shapes how opponents allocate resources and restricts their freedom of movement. Submarines do not need to fire to achieve strategic impact. The potential they carry is enough to alter decisions. The progression of submarine weapons in 2025 is best understood as an expansion of roles. From hunting submarines with heavyweight torpedoes to conducting long-range precision strikes with cruise missiles and preparing for the possibility of hypersonic capabilities, each system widens the sphere of influence a submarine can project. Rather than designing a vessel for one purpose, the Navy employs submarines that can threaten across domains, from open ocean fleet battles to inland strikes on an adversary's infrastructure. In this way, advances in weapon systems have increased not only destructive potential, but also flexibility. Torpedoes, Tomahawks, and the prospect of hypersonics create overlapping options, and each one forces adversaries to plan defensively. The US submarine is not just a ship killer, not just a land attack platform, but a versatile strike asset that extends reach in multiple directions at once. Yet none of these weapons achieve their full potential without first finding the target. Submarines must listen to their environment with extreme sensitivity, identifying threats and opportunities without exposing themselves in return. This brings combat power back to an invisible contest: how well a submarine can hear in an ocean full of noise, and how well it can hide while doing so. Revolution in sonar and detection. The contest shifts next to sound itself: how submarines hear, how they avoid being heard, and how new advances are reshaping both sides of the battle. By 2025, sonar systems and detection methods have reached a level where the balance between stealth and surveillance is far more dynamic than in earlier decades. Submarines depend on silence as much as speed, and the tools for listening and hiding continue to evolve everywhere the ocean reaches. The ocean is never truly quiet. Currents flow, storms stir the surface, marine life creates pulses of activity, and commercial traffic adds a constant hum. Against this backdrop, detection is a matter of pulling a useful signal from overwhelming noise. Submarines do this primarily with sonar, but the way they employ it defines how vulnerable or hidden they remain. Traditional sonar divides into two categories, active and passive. Active sonar sends a pulse of sound into the water and builds an image from the returning echoes, much like radar. It is reliable, but it also gives away the user's position, which is a dangerous trade for a submarine that depends on secrecy. Passive sonar listens only, capturing noise from the environment without emitting sound of its own. It is the stealthiest method, though active still has its roles for target confirmation and training. In real operations, crews rely most heavily on passive listening, arrays to stay undetected while still gathering intelligence. This task, however, is complicated by the ocean's natural clutter. The sound of ship engines, waves hitting coastal cliffs, moving ice masses, and even volcanic activity adds to the background. In earlier eras, sonar operators had little more than headphones and their own memory for comparison. Differentiating a tanker from a destroyer came down to experience and instinct, with long hours spent logging subtle propeller rhythms or mechanical tones. In contrast, modern systems use advanced processing to filter and classify sounds in seconds, turning massive amounts of raw noise into intelligible data almost instantly. For the operators, this transformation has been dramatic. Digital processors can highlight faint patterns that once took hours to confirm. Acoustic models now compare live input against libraries of recorded signatures, flagging possibilities with probability rankings. Yet even with these tools, the human ear remains essential. Computers can separate frequencies and rhythms, but often only an experienced sailor can judge if a subtle shift means a vessel has changed speed, altered course, or begun an unusual maneuver. The balance of machine and human judgment is what allows submarines to translate raw ocean noise into actionable intelligence. Quieting a submarine's own noise has proven just as important as interpreting what comes in from outside. In older designs, machinery like pumps or torpedo loading systems competed directly against sensitive listening gear, masking faint contacts with vibrations from the boat itself. Today's submarines use isolation mounts, redesigned piping, and hull coatings that absorb outgoing sound. Even the reactor system has been tuned for smoother water flow to avoid turbulence that could betray movement. By engineering silence into every component, designers ensure that the submarine can remain undetected while maintaining full operational capability. At the same time, adversaries are building surveillance networks to offset that advantage. Strategic choke points can host chains of seabed sensors that relay acoustic data to shore facilities. Moving through such monitored corridors presents its own dangers, as even the faintest anomaly may be flagged. Combined with satellite communications, improved processors, and artificial intelligence, entire ocean regions are being reshaped into monitored grids rather than untouched expanses. For a submarine tasked with slipping through, the challenge has grown increasingly complex. Industry and navies are now fielding AI-enhanced processing, lightweight deployable towed arrays, and unmanned sonar platforms that change the detection landscape. New sonobuoys and compact sonar packages are being deployed by a range of forces, with research from firms like Ultra Maritime, Aselson, and Sonartech showing how rapid the progress has become. For submariners, this means entering areas where the water itself has ears, distributed, mobile, and harder to predict than a single listening post or ship ever could. Consider an operator at watch. A faint pulse surfaces on the spectrum, low and rhythmic, 3 beats followed by a pause. The display aligns frequency lines, the pattern repeating at expected intervals. Against an ocean filled with static, this regularity tells a story. That sound could be the distant churn of a ship's propeller hundreds of miles away. Identified, tagged, and stored, such a contact may later reveal fleet movement or confirm a formation's position. In this way, listening quietly becomes as valuable as firing a weapon. Training such an ear takes years. Operators develop the ability to separate useful signals from clutter, to tell when one beat stands apart from ocean static. Technology supports them. Modern systems cross-reference against huge databases and offer identification suggestions, but final recognition comes from human judgment. Mistaking natural noise for a vessel or dismissing a contact as irrelevant could mean the difference between escape and detection. As processing power gets faster, the reliance on crew intuition remains unchanged. Detection range has expanded alongside these advances. Towed arrays and hull sensors, coupled with improved filtering, let submarines hear propeller signatures at distances unthinkable to earlier generations. This reach allows a single attack submarine to track movements not just of a single target, but sometimes an entire naval group, feeding valuable intelligence back into command networks. The information gathered invisibly beneath the surface influences fleet planning at a scale unseen to anyone outside the chain of command. But the other side benefits too. AI-driven analysis across global networks can pull together subtle inputs from vast arrays of sensors. What once was a one-on-one contest between hunter and hunted now involves system-of-systems competition where single anomalies may be enough to trace a patrol. Submarines thus rely even more on quieting, careful navigation, and the unpredictability of movement to stay hidden. Silence itself becomes an active defense, masking presence within the background noise so completely that no automated system can be fully certain. For 2025, the revolution in sonar and detection lies in this dual shift. Submarines can hear farther and clearer, while adversaries can cast wider surveillance nets. Both sides are investing heavily, knowing that detection or its absence decides survival long before weapons ever launch. In undersea warfare, persistent listening is not a supporting function, it is the battle itself. And while sound remains the front line of concealment, another question looms about the unseen edges of submarine capability. The strength of the hull and the depth it can withstand reveal the other extreme limit of survival, a boundary every sailor wonders about but few outside the service ever fully know. Hull design and diving capabilities. In discussions of submarine design, attention often turns to the pressure hull, because how deep a vessel can safely dive is shaped entirely by the material and geometry of that structure. Diving depth remains one of the most tightly guarded secrets in undersea operations. Official figures are never released, and for good reason. If adversaries knew the exact maximum depth of each class, they could exploit it tactically. Secrecy forces uncertainty. An opponent cannot be sure whether a submarine has already passed below their sensors or still lurks somewhere within detection range. That ambiguity is a defense in itself. What we do know comes from public physics and engineering principles. Water pressure rises by about 1 atmosphere for every 10 meters, or roughly every 33 feet, descended. At just a few hundred meters, that force becomes immense, pressing evenly in every direction against the hull. The outer form must absorb this with no weak points, no edges that can crumple, no seams prone to opening under stress. This is why submarines use a cylindrical cross-section capped by rounded ends, a geometry that spreads pressure consistently and leaves no flat plane vulnerable to buckling. The material used is just as critical. Generations ago, submarines relied on high-strength steels that were breakthroughs for their era, but are now surpassed by newer alloys. Modern steels incorporate carefully balanced compositions with improved tensile strength and resistance to fatigue. They are tested repeatedly for performance under cyclic stress, ensuring that a hull can endure countless dives and returns without gradual cracking. While experimental use of composite materials has been explored in non-structural areas, such as for acoustic dampening or lightly loaded panels, the backbone remains steel. Nothing else has yet matched its strength and predictability under crushing ocean pressure. Every operational submarine is built with 2 sets of limits. The first is the maximum routine operating depth, where it is expected to spend most of its patrols safely. The second is the deeper design limit, the point engineers have calculated the hull can still withstand under emergency stress. This buffer gives commanders options. In hostile waters, a sudden maneuver into colder thermal layers at greater depth can temporarily confound sonar tracking and help escape a weapon. That option exists because the hull is built to survive beyond what is normally demanded. Crews learn these parameters in training without ever being told precise classified numbers, always aware of the margin, but never revealing it. Emergency procedures reflect the absolute importance of hull integrity. The most dramatic is the ballast blow. If a submarine needs to reach the surface quickly because of flooding or damage, compressed air is forced into its ballast tanks, driving out seawater and restoring buoyancy. Sailors call the manual initiation switches the chicken switches, a reference heard across Submariner accounts. When pulled, they set off the emergency blow, a violent surge that drives the boat upward with startling acceleration. Every submarine crew practices it in drills. Modern systems have computer-regulated valves and carefully designed flows to make the maneuver safer than in earlier decades. But even now, the experience is rough. Surfaces tilt sharply, unsecured items fly, and the whole vessel shudders. Crews train repeatedly to execute it calmly, because in the rare case the hull's strength is threatened, there may be no other way out. Hull depth performance is not only about surviving disasters, however, it also enhances tactical flexibility. A submarine that can descend deeper gains more choices in how it navigates and hides. Thermal layers, where temperature changes alter the path of sound, often occur below what earlier designs could reach comfortably. With stronger hulls, today's submarines can exploit these layers consistently. The result is an ability to break contact, reposition unseen, and return to shadowing targets without exposure. Diving depth is as much a tool of evasion as any noise reduction technology. Beyond strength, the hull serves as part of the submarine's stealth system. Smooth exterior lines reduce turbulence and flow noise as the ship moves. Coatings and specialized acoustic tiles applied to the outside absorb sonar pings rather than reflect them, turning what could be a sharp echo on an enemy display into little more than a faint blur. Designers understand that survivability is not just about preventing the sea from crushing the vessel. It is just as much about preventing detection. The hull provides both simultaneously. Even in routine patrols, depth matters. By operating below the layers most crowded with surface traffic, submarines avoid not only accidental detection, but also interference from civilian noise. The further they dive, the clearer their listening environment becomes. Modern metallurgy and design allow prolonged operations at such depths without the creeping risk of fatigue-induced cracks that earlier submarines faced. Before commissioning, every new hull undergoes extensive pressure testing, often cycling loads many times to simulate years of diving. The process weeds out weaknesses before the vessel ever sails operationally. For the sailors inside, awareness of the hull's role is constant. Watch officers always know the limits, where safe operation ends and where the design envelope begins. That knowledge is not abstract. It shapes decisions during tense situations. A captain deciding whether to dive for concealment does so knowing the margin is there by design. The crew trusts that the structure around them can take what the ocean delivers, tested and measured long before their deployment. Still, no submarine is invulnerable. Emergency flooding drills, compartment isolation, and quick response to any breach remain standard parts of daily readiness. Over the years, pressure and stress gradually take their toll. Steel is tough, but it changes under decades of cyclic loading. That is why every submarine is inspected on strict schedules. Non-destructive testing methods look for fatigue cracks hidden beneath coatings. Maintenance cycles replace fittings, repaint, and reseal surfaces, and confirm strength against the original baselines. Eventually, however, even the most advanced hull reaches the end of safe service life. Nuclear reactors might have decades of fuel, electronics can be upgraded, and combat systems swapped. But if the pressure hull is no longer reliable, the submarine has no future at sea. The hull sets the real expiration date. That fact underscores its silent importance. The pressure hull may never fire a weapon or track a contact, but it stands as the foundation on which everything else depends. It resists the ocean's crushing weight, enables deep maneuver and shields the submarine from active sonar. Without it, propulsion, sonar, and weapons would be meaningless. With it, they become the tools of a functioning warship. The hull is the reason every sailor aboard can carry out their mission in the first place. And while engineering makes that survival possible, life inside those hulls tells a different story. Beyond the calculations of alloy strength and emergency drills, crews endure months in confined conditions where the pressure comes not just from the ocean, but from the routines and strains of daily existence at sea. Life aboard in 2025. Life aboard in 2025 is less about high drama and more about enduring a highly structured routine inside an environment with no natural light, no fresh air, and almost no privacy. The outside world may shift with seasons and sunlight, but inside the boat, time is carved into watch schedules and rotations that dictate when each sailor eats, works, and sleeps. A study of submariners underway found they averaged about 6.6 hours of sleep per day, compressed into shifts that rarely aligned with a normal day and night cycle. Fatigue builds quickly, but discipline keeps the crew synchronized. Personal space is practically non-existent. Passageways are narrow, bunks are stacked 2 or 3 high, and the submarine's complex piping and wiring take up every bit of available space. Most sailors sleep in what they call a rack, hardly bigger than the body itself, with just enough room to turn on one side. Privacy isn't an option. To solve the shortage of beds, crews often rely on hot racking, where 3 sailors share 2 bunks in rotation. When one finishes a watch, another climbs into the still warm bedding. What would sound unpleasant ashore becomes routine in practice, another part of the life every submariner accepts from day one. Rituals and morale practices make the routine bearable. Meals are the anchor of each day, a predictable moment when the crew gathers for something more than calories. The galley, the submarine's closet-sized kitchen, prepares 3 meals a day for more than 100 people. Limited space and storage force menus into predictable cycles, but small treats break the monotony. Friday night pizza, hamburgers from the grill, or even a rare batch of ice cream become highlights everyone talks about afterward. These little breaks are remembered long after the mission's end, because they punctuate the grind with comfort. Special touches from cooks are more than food, they are morale events. Workloads remain constant in every free space of time. Every sailor, no matter their specialty, handles maintenance. Pumps, valves, electrical boards, and ducting require routine checks, and preventive upkeep becomes a rhythm as essential as standing watch. Even off-shift, assignments continue. Cleaning, repair work, updating logs, or training. There is little true downtime. When sailors climb into their racks, the hum of machinery is inescapable, but most can sleep through it, rocked by the familiarity of the submarine's noise. Silence simply doesn't exist in a machine that never stops running. The makeup of crews has shifted in recent years. For much of their history, submarine crews were almost entirely male. Today, women serve across both officer and enlisted roles, integrated fully into submarine life. Adjustments to spaces and berthing arrangements now allow mixed crews while preserving what privacy is possible under tight constraints. For the sailors themselves, this change has simply expanded the pool of capable talent, and mixed-gender crews in 2025 no longer stand out as unusual. Professionalism and discipline rule daily interactions, because in conditions this close, everyone is judged first on their competence. Connectivity has also changed compared to earlier decades. Submariners cannot stream movies or send constant texts, but limited digital resources are built directly into ship systems. Interactive modules allow training refreshers or simulations during off hours, replacing what once required classroom instruction ashore. Secure connections occasionally allow bursts of email, giving sailors a brief line back to families. The world remains far away, but these rare touches ease what was once total isolation. Even knowing a brief note from home may come through as an outsized effect on morale. Handling the pressures of confinement requires constant structure. Conflict and frayed tempers are inevitable when more than 100 people live in such close quarters, but order is maintained through precise scheduling and long-standing traditions. Field Day, a ship-wide cleaning where every hand participates, keeps spaces sanitary and safe while reinforcing collective discipline. Physical exercise is another outlet. A few pieces of equipment, often a treadmill or stationary bike in a narrow corner, provide a way to burn energy and fight the stresses of confinement. Even 10 minutes of exertion can reset focus. Leaders encourage these habits because they directly preserve performance in the demanding environment. The mental strain is real. A submarine measures only a few hundred feet from bow to stern, and after several weeks, that limit weighs heavily. Fatigue makes tempers short, and sailors sometimes retreat into isolation, headphones on or rack curtains drawn. Officers and senior enlisted watch for these patterns carefully. In an environment without natural breaks, leadership creates small ones deliberately. Whether it's a movie night, a morale treat in the galley, or a few minutes of email access during a secure connection. These pauses in the grind carry outsized weight. From these routines arises one of the most valuable assets of submarine service: camaraderie. Every sailor aboard lives through the same watch cycles, eats the same food, shares the same frustration when mail is delayed or repair work drags past midnight. Hot racking, long drills, endless maintenance. They sound unpleasant, but they become the glue holding the crew together. Everyone endures them, and that shared hardship builds bonds that carry into civilian life long after service ends. Submarine sailors often remember the company more than the missions themselves. Details of deployed traditions further reinforce that bond. On holidays, crews might receive a special meal or dessert. Captains occasionally allow a short morale broadcast over the intercom, a song introduced just to break routine. Surfacing after months submerged, when the first whiff of fresh air hits, is a sensory milestone sailors remember for years. These moments act as anchors in a world where time blurs, small reminders of humanity inside the machine. Life under the ocean in 2025 is therefore a balance. Long watches, little space, and constant demand countered by shared rituals, updated connectivity, and bonds that exist nowhere else. Individual discomfort is constant, but the collective carries the weight together. Tiny gestures, like a pizza night or a long-awaited email, feel enormous because of how rare they are. Those tiny rituals, a slice of pizza on Friday, a short note from home, are the social oxygen that keeps the mission alive. And behind this endurance lies another truth. Maintaining a submerged city powered by a nuclear reactor and armed with live weapons is an unforgiving job. Crews kept sharp not only through discipline, but also through preparation, drilled in every imaginable crisis before they ever set foot aboard. Training the Submariners. Training the people who serve aboard submarines is as demanding as the missions themselves. It begins long before any sailor ever steps inside a steel hull. Entry into the submarine community requires a process designed to measure not just intelligence and technical skill, but the ability to function under isolation and unrelenting pressure. Only those who meet both standards proceed, because life underwater demands precision in an environment where hesitation can be fatal. Selection is deliberate. Candidates undergo academic screening and psychological evaluation before being accepted. The testing doesn't stop at book knowledge. It probes for resilience, judgment under stress, and comfort with confinement. It isn't enough to excel at equations or memorize schematics. A submariner must be trusted to make clear decisions when fatigued and to work seamlessly with others in close conditions. Those who show skill but lack the right temperament are reassigned early. The force cannot risk emotional volatility or lapses in judgment when the margin for error is so thin. Academic training then builds the technical foundation. Sailors bound for nuclear propulsion complete Naval Nuclear Power School, where they study atomic theory, reactor control, chemistry, and thermodynamics at a pace most describe as relentless. Graduates then move on to hands-on prototype training, operating full-scale training reactors under instructor supervision to translate theory into practice. For those assigned to weapons, navigation, or sonar, a parallel school pipeline covers combat systems, sound propagation, navigation charts, and fire control fundamentals. In both cases, the approach is the same: weeks of immersion, constant quizzes, and high attrition. The goal is not to carry every recruit forward, but to ensure that only those who can handle technical mastery under pressure progress to see duty. Classroom learning, however, is only one layer. Submarine training pivots on what happens inside simulators that replicate the chaos of emergencies. Candidates sit in mock compartments with controls identical to those on real submarines, facing crises that could arise during an actual patrol. One exercise might simulate a fire in a machinery space. Thick smoke fills the compartment, emergency lights flash, and sailors, restricted to breathing masks, must locate and extinguish the source before the heat becomes overwhelming. Another places them in a flooding trainer where water roars into a compartment from multiple ruptures. Here, the drill enforces a lesson from decades of experience: patch the lowest holes first, or the entire space will flood beyond recovery. Students learn quickly that these decisions must be made under pressure, and hesitation is punished with failure. By 2025, simulators are far more adaptive than those of past decades. Many incorporate AI that varies conditions in real time, so no two drills unfold the same way. If students respond quickly, the system raises difficulty, forcing them to juggle multiple failures in parallel. If they misdiagnose a valve alignment, the simulator compounds the error into a cascading fault. This removes the predictability of rote practice and builds instincts that can adjust to the unexpected. Instructors no longer test only procedure. They test adaptability and calm under escalating stress. Reactor operators in training face some of the hardest scenarios. Digital platforms replicate the full control room of a submarine, right down to the feel of switches and panels. An instructor can simulate a pump failure, a sudden spike in reactor power, or chemical imbalance in the coolant loop. Messages flash, alarms sound, and students must analyze the situation instantly. Respond too slowly, and the system trips into a shutdown, recorded as operator failure. The repeated lesson is clear: caution matters, but hesitation can be just as dangerous. Future engineers carry those early impressions into their whole careers. Combat systems trainees receive an equal baptism. Before ever hearing a real sonar contact in the ocean, they practice in simulated waters filled with background clutter. AI tools recreate conditions ranging from Arctic ice churn to the dense shipping lanes of the South China Sea. Against this noise, candidates are required to isolate faint acoustic patterns: the subtle whine of a propeller blade, the cyclical rhythm of a merchant ship, the irregular cadence of a submarine pump. Early in the pipeline, these distinctions blur together. With time and practice, operators build the specific kind of patience and focus that makes the submarine effective in contested waters. Yet the design of these drills goes further than teaching equipment. They condition sailors to remain functional while overloaded. Instructors deliberately schedule training to overlap with fatigue. Watches during school mimic those at sea, irregular and repetitive, designed to push candidates beyond comfortable sleep cycles. A sailor stumbling through a drill at 3 a.m. learns what it feels like to react while exhausted, because that is the reality of operations underway. Psychological screening ensures the right personality is present. Training puts that resilience to the test. This process produces a certain culture. Submariners often describe themselves as meticulous rather than flashy. Every system inside a submarine is linked to another, and shortcuts are not tolerated. Students come to understand how atmosphere purification links directly to reactor output, how sonar operations depend on electrical circuits, and how weapons loading requires coordination with multiple safety systems. Training pulls all of these together into cascading simulations, teaching that failure to communicate across specialties causes the entire boat to fail. Precision and teamwork are not ideals, they are survival mechanisms. Graduation from school and simulator training does not end the process. Drills continue aboard the boat from the first deployment onward. On patrol, officers run unannounced exercises daily. A ventilation fan suddenly smokes, an alarm shouts flooding in the engine room, or a combat screen flashes the trace of a potential hostile torpedo. Crew members react instantly. They have no choice. That constant repetition ensures sharpness, and it reminds everyone on the crew that complacency is the first enemy. The cycle never stops because the conditions of submarine service never ease. The effect is cumulative. By the time a sailor earns a place in the fleet, they have already experienced fires that could not be seen through the smoke, flooding drills where compartments nearly filled, and reactor malfunctions demanding precise shutdown steps. They have faced all of these while tired, hungry, and supervised by instructors determined to catch each hesitation. The result is confidence, not the naive confidence of never having struggled, but the practiced calm of someone who has failed in simulation, learned, and improved. This confidence is why the submarine force invests so heavily in training as a filter. Mistakes made in training save lives later. Instructors accept no excuses because the ocean itself will not grant second chances. Only those who can demonstrate control under pressure advance. Training molds not just technical skill, but a mindset that treats every alarm as urgent, every reading as vital, and every procedure as non-negotiable. Submariners carry that conditioning into every patrol. By 2025, the outcome of this pipeline is clear. Those who reach the fleet are not simply students who passed exams. They are operators conditioned to handle fire, flood, and reactor emergency with a steady hand. They operate sonar with practiced patience, calculate firing solutions under stress, and maintain propulsion plants with constant vigilance. They know fatigue will shape their choices, but they have already proven they can perform while tired. The hours in classrooms, simulators, and never-ending drills at sea yield a crew able to sustain sharpness inside a hull that may remain submerged for months. Still, preparing the people is only one half of the equation. The machines themselves, the enormous nuclear submarines, require years of construction and relentless cycles of repair to remain in service. That challenge unfolds on an industrial scale, and in many ways it is just as decisive as the human preparation behind it. Construction and maintenance challenges. Building submarines is not just an engineering task, it is an industrial commitment measured in years. Modern attack submarines typically require 5 to 9 years from the first cut of steel to commissioning, while ballistic missile boats demand even longer. For example, the Columbia-class lead vessel has already faced delays of 12 to 16 months in recent reviews. These long horizons stand in stark contrast to the relative speed of training new sailors, and they create bottlenecks that shape how many hulls actually reach the fleet in time to meet rising demand. The scale of these projects explains the timeline. A Virginia-class submarine, the backbone of the attack fleet, averages 6 or 7 years in construction. Once the keel is laid, workers must fabricate and join hundreds of pressure-resistant steel sections, thread miles of cabling, assemble propulsion systems, and carefully install the nuclear power plant. Every weld, valve, and circuit is scrutinized under inspection standards that allow no tolerance for error. Larger ballistic missile submarines, like the Columbia class, add another layer of complexity with missile compartments, secondary reactor shielding, and redundant safety systems. The scope turns construction into a decade-long enterprise. Production is concentrated in only a handful of US yards. Roughly 7 shipyards handle most submarine construction and maintenance, and many critical components have no competing suppliers. That fragility means production rates cannot be scaled up quickly, even with political will and funding. A delay from a single supplier may cascade into months of shipyard idle time. Skilled labor adds another constraint. Welders certified for submarine hulls, nuclear technicians, and defense electronics electricians are not workers that can be trained overnight. It takes years to build the expertise each role demands, so expanding the workforce is always slower than the pace of contracts or budgets might suggest. Shipyards themselves resemble cities dedicated to submarine construction. Work proceeds in shifting crews around the clock, overseen by teams with decades of specialized practice. In many industries, inspection checks are designed to catch problems at the end of a process. In submarine yards, inspections happen at every stage. Discovering a crack in a weld or misalignment in a pipe fitting does not just slow work, but compels a full teardown and rebuild of that section. These high standards inevitably stretch schedules, but are necessary because small mistakes at sea could prove fatal. Even once built, submarines cannot remain constantly available. Maintenance cycles tie up a significant fraction of the fleet at any given moment. Annual upkeep pulls boats briefly out of service, while scheduled overhauls, especially reactor refueling or midlife upgrades, can tie a submarine to a dockyard for 18 months or more. These yard periods are essential to keep reactors safe, hull coatings effective, and sonar or combat systems current. Without them, stealth and reliability would erode well before a submarine's projected service life. Yet the effect is unavoidable. Ships counted in the official fleet may not be deployable when needed. This distinction between, on paper, fleet size and the boats actually available shapes deployment planning in tangible ways. While the US might list around 64 nuclear-powered submarines in its inventory, maintenance cycles reduce the number that can actually patrol. In practice, fleet planners often have only 40 to 45 boats available worldwide at a given moment. The rest are consumed by yard time or mandatory training. With global missions stretching across the Atlantic, Pacific, and Arctic regions, those 45 are rotated heavily, adding strain to both machines and crews. Strategic submarines face an even stricter standard. Because they carry nuclear weapons, their maintenance periods require exhaustive checks of safety, reactor integrity, and missile system readiness. A delay in bringing a Columbia-class into service, or keeping an aging Ohio in dry dock longer than planned, creates the risk of a deterrence gap. To maintain continuous patrols, a cornerstone of nuclear strategy, each refit and inspection has to line up precisely. Even brief delays ripple through global planning, creating flashes of vulnerability that adversaries will note. All of this underscores that the submarine fleet's reliability depends as much on its industrial foundation as on the crews who sail it. Shipyards and suppliers act as strategic assets. Their ability to keep work flowing steadily is a form of national defense in itself. Protecting that industrial base means ensuring the stability of the workforce, guaranteeing supply chains for reactor components and acoustic materials, and investing in dry dock facilities that can support multiple submarines at once. Any weakness in that industrial chain reduces fleet readiness just as surely as a failed component at sea. Budget plans often call for ramping construction to 2 attack submarines per year, but the capacity of the shipyards continues to fall short. Actual delivery rates have averaged closer to 1.2 Virginias annually, creating a persistent gap between goals and output. That disparity compounds over time. Submarines age out of service faster than replacements arrive, shrinking the available pool. Policy discussions about numbers on budget charts cannot gloss over this reality. An industrial bottleneck today becomes an operational shortage tomorrow. For sailors stepping onto a newly commissioned submarine, the years of hidden work behind it may not be obvious. But for strategists, those hidden years define the fleet's limits. Every weld completed on time, every part delivered without delay, carries forward into the map of where submarines can operate in 2030 and beyond. The industrial base is not just a background process. It determines which oceans can be patrolled, which threats can be shadowed, and how continuously America can sustain its presence underwater. That leaves a fundamental tension. Even the most advanced hulls and weapons are constricted by the slow pace of industrial capacity. Shipbuilding and maintenance delays do not remain confined to dockyards. They translate directly into presence gaps at sea. Adversaries track those gaps carefully, watching not only what sails, but what fails to sail. For a force that relies on invisibility and ambiguity, losing coverage in critical waters erodes both deterrence and confidence. Submarine design and strategy lean on the promise that an adversary can never be sure where the next boat might be. Industrial bottlenecks narrow that uncertainty. In some, construction spans many years, maintenance locks vessels in dockyards, and limited shipyards set a ceiling on how fast the fleet can grow. These are not abstract issues. They are operational constraints with strategic weight. Decisions made in the industrial base today shape fleet posture for decades to come, influencing which missions are sustainable and which must be risked with fewer hulls. And just as timetables and supply chains shape submarine strength from within, so do the capabilities rising outside the fleet itself. While the US struggles with construction pace and maintenance cycles, adversaries are developing ways to challenge the very invisibility submarines have long relied on.
you